Welcome everybody to the webinar this morning if you're in the UK, or this afternoon if you're in India. And today just going to talk about the use of gas generators for GC applications, particularly focusing on the safety, reliability and convenience of gas generators. So just to give you a quick outline of the webinar, first going to look at helium in terms of the current global situation and outlook. Look at helium conservation, and then look at nitrogen and hydrogen as carrier gas, and then talk about why it's beneficial for your lab to use a generator, and then look at in more detail at the precision generators before looking at a couple of application examples using hydrogen and nitrogen as carrier gases. So the current situation with helium, I'm sure many of you attending the webinar are aware that there's been an increase in price over the last couple of years in terms of helium cylinders, and in fact that price has almost doubled in some regions of the world, and so there's increasing pressure on labs to look for alternatives. The current supply for Eurasia really centres on supplying Qatar and North Africa. Also, there are some stocks in Russia. So if you look at the figure on the right-hand side, you can see the world reserves. The USA having the vast majority of reserves, but that's mostly the supply from those reserves is mostly concentrated within the US. The cost of helium is set to increase as there's a cost to refining the gas, which normally occurs within natural gas deposits, and there are calls for priority use for liquid helium users. Again, if you look at the figure on the right hand side, it shows in the balloons there the consumption of helium, with the vast majority of helium being used for applications such as cryogenics, welding, party balloons weighing in at 8% of consumption. Apparently this is now dwindling, and I'm sure many of you, if you're using GC, you see that you sit within the analysis balloon there, so with a total consumption of around 5% of global helium. So when it comes to distribution of the available helium, you can see why it can be GC labs to get supply. So there needs to be a look for alternatives wherever possible. Now, I stole this figure from Agilent from a presentation they did a couple of years ago. It's basically looking at the use of helium or alternatives for labs. And you see on the left-hand side, helium conservation is highlighted. So in terms of applications where the customer is unwilling or unable to use an alternative to helium, then helium conservation is something that they should consider. Whereas on the right-hand side, you see if they're using GC or GCMS, there are the options to move to nitrogen or hydrogen. And this is something we'll explore in more detail. In terms of helium conservation, this is really something that many labs look at for applications where its use is essential, or where methods allow no alternative. Obviously, many labs use regulated methods where they may stipulate the use of helium, so they don't have an alternative to change to hydrogen or nitrogen carrier gases, and so therefore their hands are effectively tied. But there are an increasing number of methods that have been revalidated for use with hydrogen and nitrogen, and I've just got the example here of an ASTM SIMDIS method, which is actually available for the use of both hydrogen and nitrogen as alternatives to helium. In terms of the alternative carrier gases, if we look first at nitrogen, it's generally seen as a slow carrier gas, as it has a low optimal velocity of 8 to 14 centimeters per second, but it's cheap and it can be produced by gas generators, which obviously has some advantages. Hydrogen is often cited as a fast alternative to helium, as it has a high optimal velocity. Again, it can be cheaply produced, and it's available from gas generators, but there is the perceived danger of hydrogen. Again, this is something I'll touch on later in the presentation. Looking more closely at nitrogen as a carrier gas, I'm sure many of you in India are perhaps using nitrogen already, and so some of this won't necessarily be new information, but I'd just like to illustrate the virtues of nitrogen. With sufficient resolution, you can afford to lose some plates. So if you look at the Van Diemter curve on the right-hand side of the screen, you see the HETP, which is the plate height, and you'll see how this varies as you increase the velocity of the carrier gas. Now with hydrogen, this drops off less quickly as opposed to with nitrogen. And so what happens is that as you run the gas at a higher velocity, you will lose plates, or you'll increase the plate height, which will mean that you have a resulting loss of efficiency. Now, if you've got enough separation between the peaks in your chromatogram, then this is usually okay. And as you can see, I've highlighted the difference between the nitrogen and helium plate height here, where with nitrogen running at around the same velocity of helium, the plate height is doubled. So your HETP is increased by a factor of 2. Now, this loss of efficiency by a factor of 2 only means a loss of resolution by a factor of 1.4. So the loss of performance is not as stark as it may first appear. Moving on to hydrogen. Hydrogen is already present in many labs if they're using FID detectors or other detectors that use a flame. And hydrogen offers the potential for improved efficiency. Peaks are twice as high as with helium, and this can have advantages in terms of reducing maintenance on the system, because you can inject less sample onto the GC, which means that you're going to have to change your liner less often, and you can potentially increase throughput to a level of twice that of helium. So there are big gains to be made for any contract labs who are basically charging per sample. Now at this point, I'd just like to pause for any questions that you may have. So if you'd like to use the raise hand function if there are any questions. Okay, that doesn't appear to be the case, so I'll just move on. Okay, so now I'd just like to look at this table where we just have some comparisons between gas generators and cylinders. So why would you want to use a generator rather than cylinders? So in terms of convenience, gas generators produce gas on demand with a consistent purity, and the systems available from Peak Scientific are stackable, so you can have 3 gases from one stack, which takes up quite a low footprint in the lab. And once installed, the system only needs to be maintained on a either half-yearly or yearly basis, depending on the system. If we contrast this with cylinders, which need to be monitored so that you don't run out of gas in the middle of analysis, you also need to order them on time so that you have ready supply, and you also have to move them around, which has potential health and safety issues. Purity. Gas generators produce a consistent purity of gas, whereas cylinders can have inconsistent purity from cylinder to cylinder, since cylinders are only batch tested. So it's possible that you could get the bad apple in the batch. In terms of economy, gas generators offer a fast payback or return on investment. You have low ongoing costs, so once the system's installed, there's very little in terms of cost of ownership, and you have 24/7 gas production. Contrast this with cylinders, where you're at the mercy of the cylinder company in terms of delivery costs and cylinder rental. And you also have the issue of instrument downtime when you're changing cylinders, and the risk of introducing contaminants. In terms of safety, gas generators have a very low stored volume at relatively low pressure. And if you compare this to gas cylinders, which typically have around 8,000 to 9,000 litres of compressed gas at 200 bar pressure, when they're full, then there's a potential health and safety issue with storing them in the lab. And then there's the environmental aspect as well. So gas generators, once they're delivered and put into the lab, they don't need to be moved around, so you have potential for reduced carbon footprint. Whereas with gas cylinders, they need to be transported by road, often over large distances, and this can occur many times per year. Now, the main focus particularly when we look at hydrogen, is safety, and so I'll dwell on the safety aspects of our hydrogen generator afterwards. Again, if you have any questions, please use the raise hand function. Otherwise, we can, if any questions come, we can address those at the end. Okay. Oh, hello? No? Okay.
Unmuted.
Right, so now I'll just give you a quick overview of the precision hydrogen trace generator. So this is a
Muted.
gas generator that produces hydrogen on demand, which is suitable for carrier gas, detector gas, or reaction gas, depending on the application that you need to supply. And this system produces hydrogen at 6 nines purity. It has an internal leak detection system so that it's monitoring the pressure within the generator to make sure that there's no leaks within the system. And it has an automatic safety shutdown feature so that if there are any leaks between the generator and the application, it will shut down, as well as having forced air ventilation within the system so that if there was a leak of the hydrogen or oxygen into the generator, this is purged from the system. Now, we generate the hydrogen using a proton exchange membrane, or PEM cell, and what we do is we take in deionized water from an external water bottle, which is pumped into the cell, and by applying electric current to this, we separate the water to its constituent hydrogen and oxygen. And then we take the hydrogen and further purify this using a dryer called a PSA, or pressure swing adsorption dryer. In terms of maintenance, the generator has very low maintenance, requiring just a change of a deionizer cartridge every 6 months. And the system is operated via a touch screen, which you can see on the figure there on the top right of the generator. And it's very easy to use, so it's just a touch screen, very intuitive menus, and it's very easy to start up and shut down. A single unit has a maximum capacity of 500 cc's per minute, but what we can do is, to increase capacity, we can link multiple units. So if you needed a litre or 1.5 litres, we could link 2 or 3 systems which would work on a master-slave configuration, and they would share the output of gas required by the application. Peak offers a 3-year standard cell warranty across all the hydrogen generators, and to our knowledge, this is the best on the market. So just to go over a couple of the safety features again. When we start the generator up, it conducts an internal leak check, so it will pressurize the system and make sure that there are no internal leaks, and make sure that it can hold the pressure. The external leak detection means that if there was a leak between the generator and the GC, for example, after 20 minutes, the system would shut down. So that this prevents any buildup of hydrogen in the lab or in the GC itself. As I mentioned before, we have the forced air ventilation to prevent a buildup of hydrogen or oxygen in the case of an internal leak. And we also monitor the pressure throughout the system to make sure that we don't have low pressure or indeed too high a pressure. In the case of any pressure issues, we have a mechanical shutdown of the cell, and we also have audible and visual alarms via the screen. Now, just a quick point on hydrogen safety, because this is one of the questions that we're asked most often, is about the explosive nature of hydrogen. Now, hydrogen is a flammable gas, and it has a lower explosion level of 4.1% in atmosphere. So just for example, here we have a room measuring 5 by 5 meters with a 2.5 meter room height. This room would contain 50 cubic meters or 50,000 liters of air. So the LEL for hydrogen would be just over 2,000 liters. Now, if you had a cylinder in this room and rapidly released the contents of the cylinder, you can see that you'd very quickly reach the LEL by releasing just a quarter of the contents of the cylinder. If we contrast this with a hydrogen generator producing 500 cc's per minute, it would take almost 3 days to reach the same level of hydrogen. And this would mean that you'd have to avoid any escape of the gas, which is very diffuse. So I think this illustrates nicely the safety aspects of using a hydrogen generator in the lab. Are there any questions relating to the hydrogen system or the use of hydrogen at all? No? Then I'll move on. Okay, so now I'll just quickly introduce you to our nitrogen generators. We have 2 different grades of nitrogen, what we call standard and trace nitrogen. So on the left is the standard nitrogen, and on the right the trace nitrogen. Both systems produce 5/9 purity nitrogen using, again, a pressure swing adsorption system. And what we do here is we have a carbon molecular sieve column, which is pressurized using compressed air. And during the pressurization process, we adsorb oxygen to the CMS, carbon molecular sieve material, and allow nitrogen to pass through to a buffer tank. Then when we depressurize the system, we release the oxygen and vent that to the atmosphere. The difference between the 2 systems is that the nitrogen trace system has a catalyst chamber which removes CH4, methane. And the reason that we have this is for any applications that require CH4 free gas. This just offers better purity because you can't actually trap CH4 using gas traps. And the hydrocarbon level is 50 ppb, or 0.05 ppm. Any questions on that? If not, we'll save them to the end. And I just want to illustrate here that both the nitrogen and hydrogen systems sit of the precision range, and so we have the additional option of zero air and also a compressor which can be stacked. So the size of the stack is roughly the same footprint as 2 large cylinders. So you can see that you're getting a lot of gas from very low footprint. Obviously now labs are looking to maximize the potential of their floor space, so this is a good option for labs where space is critical. Now I'm just going to quickly look at revalidation of methods in case anybody is looking at revalidating their methods from helium to hydrogen or nitrogen. The first thing you need to do is to review your documentation to make sure that your methods comply with the use of hydrogen or nitrogen carrier gas. Then check any health and safety documentation, and also check any information from your GC supplier regarding their recommendations for the use of hydrogen or nitrogen. Then it's necessary to perform routine maintenance, for example, replacement of liners or septa. Also, if you're looking at GCMS using hydrogen, you want to make sure that you have the pumping efficiency required for the use of hydrogen. Would recommend installing new gas lines, stainless steel preferably, especially if you're using hydrogen, but copper will also do as long as it's analytical grade. And this is important because what can happen if you're using helium over time, you can get small deposits on the inside of the tubing, which you'll find when you switch to hydrogen, the hydrogen will strip out those deposits, and this will result in a higher baseline or higher background for some time. So it's best to save that effective downtime by changing the gas lines. If you're using mass spectrometer, would recommend using traps just in case of the event of a leak to prevent any oxygen getting into the system. And there are some method translation software programs available. There's one from Agilent, which you can download from their website, and there's also a ResTech method translation software, which you can either download or use online. And these are a good place to start if you want to explore using hydrogen or nitrogen carrier gas. What you can do is you can put in your GC method parameters, and you can find out what your method parameters would be using hydrogen or nitrogen. So it will reconfigure the method for you. Also reconfiguring any oven ramp rates and oven holds that you have on your GC method. So it's definitely a good place to start. If you have any more questions regarding this, feel free to email me and I can provide you with information. Now I'm just going to look at a couple of application examples. First of all, phase analysis. Now this is using or looking at the change from helium to hydrogen for GCFID analysis. And in this case, the end goal was to match the linear velocity of the gas so that the customer was getting like-for-like results when using hydrogen compared with helium. This meant that there was no need to worry about peaks changing position or any change in retention time. It was more or less a case of carrying on with the same analysis, just using a different carrier gas. As you can see from the two chromatograms at the bottom, the retention times are unchanged, but the advantage is that the efficiency is improved when using hydrogen, so the peak shape's improved and there's a better signal to noise relative to helium. Quickly just show you the detailed hydrocarbon analysis example. And by the way, all of these application notes are available on the Peak Scientific website, and I'll give you the address that you can find those at the end of the webinar. So this is an ASTM method which was revalidated or available for revalidation from helium to hydrogen. It uses a 100-meter column, and the take-home message really is that using helium, the analysis time is around 2 hours, whereas with hydrogen, the analysis time is down to 73 minutes. So you can see that there are vast time savings available to labs by going to hydrogen carrier gas for applications like this. It's also important, of course, that you're able to separate your peaks of interest, and in this case all of the peaks of interest were separated, and there was no difference found in any of the major constituents of the analysed gasoline mixture. And finally, just going to show you blood alcohol analysis, and in this case it was a headspace GCFID method and a comparison of using nitrogen and helium as carrier gas. Nitrogen was used for the headspace sampler, and in the case of nitrogen, nitrogen carrier, as well as makeup on the FID. And just one thing of note is that in this method there was a very high linear velocity used, so above 80 centimeters per second. But there were no significant results found between nitrogen when you compare it with helium. As you can see here, the calibration curves both gave very good R squared values, and if we look at the chromatograms, you're getting very similar analysis, so good separation of all of the peaks in the standard there. And this table just shows some unknown samples that were analysed using both nitrogen and helium. And so these were analysed in duplicate, and you can see that the values are very close indeed. So there was no significant difference between any of the results, regardless of which carrier gas was used. So that brings me to the end of the webinar today. As I mentioned just before, you can find any of the articles that I've just referred to on our website, and also any videos. We've got some videos regarding our products and also other application information. So thank you for your interest today, and if there are any questions, fire away. I can see. Hello.
Hey, Dr. Red, thank you very much. It was quite informative. I just have a couple of questions here, which were mailed to me from one of our customers. It says, what's the consumable need for the generator? So he's actually talking of a stack. He wants the hydrogen, air, and nitrogen gas. So he's asked for the consumables that would be required for the generator for 3 years.
Okay. So for the hydrogen trace that I was talking about, the only consumable on that is a deionizer cartridge, and that needs to be replaced every 6 months. So it's possible to get PM kits from Peak for that. The dryer on that system is completely regenerative, so it's almost a maintenance-free system. We have another hydrogen system which uses a silica gel dryer, which is suitable for FID flame gas, and on that system the consumables are the deionizer cartridge, and the silica gel needs to be either regenerated or replaced periodically. On the nitrogen and zero air systems, we only require a change of filters every year, and then if any customers are looking at using the compressor, then the compressor also needs to be refitted every 12 months. So it's across the range, it's very low maintenance.
Thank you. And I think Mr. Praveen Dixit has 2 questions here. He's asked about how do you calibrate or qualify the gas generator, and also how do you test the generated gas. So I'll just unmute Mr. Praveen so that you can interact with him. Just give me a second, please.
Okay.
Yeah, Mr. Praveen, please. I unmuted you. Hello?
Hello?
Yes, Mr. Praveen.
No, I can't hear him.
No. Okay, so the questions are, how do you calibrate or qualify the gas generator? And
Right.
how do you test the generated gas? And how do you test the generated gas?
Okay, so so all of our systems are have been developed here at Peak Scientific in Glasgow by our engineering R&D team, and so the purity of the hydrogen is determined through measurement of moisture and other contaminants within the gas. So we've got a number of different instruments that we use in-house to calibrate the systems, and prior to shipping any system, we put each system is put on test for at least 24 hours to make sure it meets the specifications that we demand from our systems.
Okay.
I hope does that answer the question? Or
I think that quite answers him, because I don't see any other question coming from him. The next question we have here is, what is the lifetime of the generator? What do you say? What is an average lifetime of the generator?
So what we would, obviously, as I mentioned before, we have a 3-year cell warranty.
Okay.
And the cell is in the hydrogen generator is the most critical part. It's the heart of the generator. So we're confident that the cell manufacturer that we use for supply is producing a good quality cell. What we would say is that as long as the customer is using good quality deionized water, what we specify is less than 1 microsiemens conductivity. If that level of water is being used, then we would expect that the generator should last at least 5 years, but we do have customers who've had generators for 10, 11 or 12 years. It's like any mechanical object. If you look after it and treat it in the right way, then it will last longer.
Okay, we have Mr. Tosif here, who's I've just unmuted. He's asked how many GCs can be connected to one nitrogen generator. Mr. Tosif?
Okay, so is this for carrier gas? This will depend on the total flow rate of each GC method. So it's difficult to put an exact figure on it because it will depend on whether you're doing split injection or splitless injection as to what kind of consumption of gas is required. When we specify a generator, we typically look at the maximum consumption per method, and then we'll calculate how many GCs are attached and take it from there. The capacity of one of our nitrogen generators is up to 1 litre per minute. So really it will depend on the carrier consumption of the method. But that's something that our sales team are trained to deal with. So if for specific questions like that, I would recommend that you contact your local sales rep, and they should be able to consult with you in terms of what the requirement is.
Sure. I think you just replied back saying that the total flow for the GC is around 60 milliliter per minute.
60 millilitres per minute, okay. So if you add into, assuming it's an FID with using makeup gas, then I would calculate with around 100 cc's per GC. So then it would depend on how many GCs there are. We have in terms of nitrogen, we have 250 cc's, 600 cc's, and 1 litre per minute. So based on those figures, you could have 2, 5 or 6, or 9 or 10 GCs attached, depending on the capacity of the generator that was selected.
Okay. Thanks. So the next question is, do you recommend the use of moisture traps? Are they actually really required?
So we would recommend to go with the trap recommendations of the GC manufacturer that you use. Now, just for example, with Agilent, Agilent would normally recommend for carrier gas moisture and oxygen traps, or you can get a carrier trap. For detectors, we would not normally recommend the use of any traps, and particularly for zero air or makeup gas, it's not normally required to use traps. But for carrier gas, I would definitely be more cautious and err on the side of caution and use traps.
Okay. So water quality for the hydrogen generator, it's important. How important is it to have a good quality water used for the hydrogen generator?
That's really essential, because if there are any ions in the water, or too many ions, what happens is that they can poison the hydrogen cell, and over time this will affect the purity of the hydrogen and can in fact mean that oxygen can break through the cell and contaminate the hydrogen. So that's why we really very strongly recommend conductivity of less than 1 microsiemens. And so if you've got a millipore or an ELGA system in your lab, this should provide the correct purity of water.
Okay. So I have a couple of questions on the cost of the standard generator. I have one on the cost of the nitrogen generator. I think we'll have to get back to them. with the specific application and work out the pricing for them.
Yeah,
So
yeah, because in terms of cost, it will depend on the flow rate and the purity. So it will depend on whether it's the standard or a trace nitrogen, and whether it's the 250, 600 or 1 litre system.
Sure. So I'll just request the customers who just requested for price that we will get in touch back with them and work out with them for the application and the pricing.
Mm-hmm. Okay.
I think that covers most of the questions asked. What is the typical ROI of a system in terms of the years?
Again, this will depend on the use of the generator. So whether it's being used for carrier gas, or whether it's being used just for detectors, for example. I can pass you across to my colleague Greg Stringfellow, who might want to elaborate a little on this.
Hi, Greg.
Hi.
I just yeah. Greg, do you need your laptop? Do I need to transfer it to you? Do you want to host it? Do I need to shift you, make you the presenter? I'll just change.
Just 1 second.
Yeah, sure.
Hi, is that okay?
Yeah, great.
Okay. The question was in relation to ROI. Yes. We have many customers using various different flow rates of generators, so it really does depend on their application, which I believe Ed was touching on. Some customers use more gas than others, and some customers do buy generators that are essentially working to their near full capacity, and some other customers buy generators with lots of room for growth in their lab, etc. So a customer, for instance, might only need 40 cc of hydrogen for a GCFID, but he might choose to buy a 450 cc generator. So when you look at that in comparison to cylinder use, then it may take a bit longer for ROI. However, if the customer needs 400 cc's of hydrogen and he's using our 450 cc generator, then his ROI will obviously be a lot quicker. So it depends from customer to customer, but we have some cases where customer has a payback within 8 to 9 months, and we have other cases where customers have payback in 3 to 4 years. It really does depend on their gas usage, really. But the cylinder costs rise and rise year on year generally, and you also have rental costs to consider, delivery costs to consider, and ultimately the cost of downtime is the main issue with cylinders, because with the gas generators you have gas on demand 24/7, so you're guaranteed the gas. Any form of downtime can cost the lab a lot of money. So in particular with commercial labs who are being paid per sample, they may have contracts which stipulate that they have to have results sent back in 24 hours or 48 hours. If they do not have gas, then you cannot run a sample. So there's the cost of downtime, the insurance to consider as well also.
Perfect. So, Greg, there is just a little more in detail about the ROI, the question in detail further. Next question is about the power supply. How much is the power requirement? And another question added to this is the longevity of the filters used.
Sorry, what was the second question there?
The first question was about the power supply.
Yep.
The power required.
Sure.
And so I think I'll take the next question after you answer this.
Okay, yeah. The power supply differs from generator to generator as to how much is being used, but we do have our generators generally in the 110 and 230 volt, but the actual power usage depends on the generator itself. So for instance, we have our precision nitrogen standard, and we have our precision nitrogen trace, and our nitrogen trace also has a catalyst chamber in it, so it will consume more power than the nitrogen standard, but they differ from generator to generator. But if any of the customers would like details on the power consumption for each generator, we can certainly send that on to them.
Sure. The next question was on the longevity of filters. Do we have? Yes.
I mean, generally, as Ed touched on, with the routine maintenance, it's generally every 12 months. So for the nitrogen, the zero air, and the compressor, there is filter changes required every 12 months. And with our hydrogen generators, we have the two options, the hydrogen trace and the hydrogen standard. The hydrogen standard and trace both need the deionizer cartridge changed every 6 months. And on the standard models, it uses silica gel to dry the gas. Now, the silica gel will saturate depending on usage, depending on how much flow, how much pressure is being used. It differs from customer to customer, but there is an indicator on the HMI screen on the generator which tells the customer when the silica gel needs changed. Now again, this can be anything from every 2 months to every 2 years. Completely depends on usage, but will differ from customer to customer. Okay. But the good thing about the silica gel is you can regenerate it twice, so you can use it 3 times, and then we would recommend changing the silica gel.
Okay. I think should answer this. Then we have Mr. Praveen Dixit asking, what is the impact of purity of gas on GC analysis?
I'll pass you over to Ed for this question.
Okay.
Yeah, so in terms of the effect of purity of gas on GC analysis, obviously oxygen has a big effect on GC analysis, and so our systems are designed to be as low in contaminants, particularly in oxygen, as possible. As I mentioned before, we'd also recommend the use of traps for carrier gas, just as a precaution. Also, moisture can also cause issues, and so that's why we recommend our trace hydrogen for hydrogen carrier gas, because the dryer works a little bit more efficiently than the silica gel, and means that there's a lower amount of moisture in the hydrogen. What happens if you get too much moisture in your carrier gas is you can get negative peaks occurring in the chromatogram, and you basically won't get good analysis. We've tested all of our systems for carrier and detector gas, and all of the application notes that are on the website and the examples I showed to you before were using peak precision generators, and so we got very good results for carrier gas there. Hope that answers the question.
I guess, Mr. Dixit. Yeah, I'll just take the next question from Mr. Narasimha Prasad, who says, how many GCs can be connected? I have to one generator, and I guess he's speaking about the zero air. I've unmuted Mr. Prasad. Okay,
for the zero air, typically an FID will be using between 300 and 450 cc's per minute. And so it will depend on how many GCs the lab has, but we have systems ranging from 1.5 litres per minute up to 30 litres per minute So that would be able to cater for a small lab with perhaps 3 or 4 GCs, up to probably 80 to 100 detectors, depending on the number of or on the amount of zero air each FID was consuming. So we really have a generator that should suit pretty much any lab.
Okay, I think I'll get back in touch with Mr. Prasad. Send you a mail with the details.
Sure. Again, all of the information on the different capacities of the hydrogen, nitrogen, and zero air generators is available on the Peak website.
Sure. There's one more question on what's the gas pressure. This is for a stack, and the question simply says what would be the average gas pressure?
Right. So on our hydrogen systems, the maximum pressure available is 100 psi, and typically a GC would require between 50 and 70. So this is definitely enough for nearly all GC applications. On our nitrogen and zero air systems, the maximum pressure is 80 psi, with the exception of the 30-litre zero air system, which has a 100 psi output. But again, all of those pressures are usually enough for the majority of applications. One additional product that we have is a nitrogen standard generator, which can do up to 100 psi, and this is aimed at any applications such as headspace, where higher than 80 psi is required.
Okay. Next question is on the moisture problem. So how is the moisture problem in the hydrogen generator taken care of? That's the moisture trap.
Yes. So when the hydrogen is produced by the cell, there's a bit of moisture present there. So the first thing we do is the hydrogen is bubbled through a thing called a separator tank, and the separator tank is full of water, and the hydrogen dumps any bulk moisture there, and then the gas is further purified by one of 2 methods. So as Greg mentioned before, we have the hydrogen standard, which uses a silica gel dryer. So the hydrogen gas goes through the silica gel before being supplied to the application. And in the hydrogen trace system, we have a pressure swing adsorption dryer, and this works where we have 2 parallel columns filled with molecular sieve, and one column is active while the other one is being regenerated, and every 90 seconds the 2 generators swap function. So while one's drying, the other's being regenerated, and then they swap, and so that those 2 columns keep swapping function every 90 seconds, and that's a completely regenerative dryer. So they're the 2 methods that we use for purifying the hydrogen.
Great. Okay. So I think there is one raised hand from Mr. Nilesh. I have just unmuted him. Mr. Nilesh, if you would like to ask your question, please. Hello? Okay.
Hello? No,
Yes,
can't
sir.
hear anything.
Hello? Okay. Okay. It will happen here. The next question is from Mr. Narasimha again, asking what is the maximum distance between the generator and the GC for it to work effectively?
Right. Well, we'd normally recommend that the generator is located close to the GC application, or the stack is located close to the application. We'd normally recommend within 10 meters, within 10 meters, but ideally within 10 feet. If we're looking at a distance of 10 meters, then what we have to do is to use 1/4-inch tubing rather than 1/8-inch tubing, and then go to 1/8-inch tubing closer to the GC. So there are possibilities for larger labs. But the systems are designed to be used within the lab. And we'd recommend that they're kept within the lab so that the conditions that the generators are stored in are also within the recommended temperature range. So between 20 and 35 degrees, and also so that the humidity levels are not moving around too much. So we normally recommend that the systems are kept between 50 and 70% relative humidity.
I hope that answers your question, Mr. Narasimha. I've just unmuted you. Would you like to add anything? The question is, even if using generators, also gas purification panel is required? And there's a continuation to the question. What if using generators also is a gas purification panel required?
So in terms of panel of traps?
I guess that's what he means.
Okay, so again, I'll just refer back to what I said before regarding looking at the recommendations from the GC manufacturer. So typically for carrier gas, using a carrier trap, but for detector gases, following the recommendations, so using a hydrocarbon trap on hydrogen line for FID, but not using moisture traps, for example, on a zero airline. That's unnecessary.
Okay, his reply saying his GCs are from Agilent and from Perkin.
So Agilent and Perkin-Elmer.
Yeah.
Yeah. So I have a guide that I would be able to provide on the trap recommendations from Agilent. I would imagine that Perkin-Elmer and Shimadzu and other manufacturers follow pretty much the same recommendations anyway. So if the gentleman would like to send an email, I'd be happy to provide that information.
Sure. Fine. So I think the next question is in the hydrogen generator. Question is the generator oxygen being pumped out?
Yes. So when the PEM cell is splitting the water, we have hydrogen and oxygen produced, and there's a vent at the back of the generator where oxygen is released. So it's vented to atmosphere. If this is of concern to any lab users, it's possible to fit a line to the outlet, to the oxygen outlet, and vent that to a fume hood. But in our experience, this is not really necessary. The amount of oxygen, again, is minimal, so there's no cause for concern in terms of the amount of oxygen being released by the generator.
Sure. I think we're really running out of time. We'll take the last question from Mr. Nilesh. He says, is the gas pressure for the gas cylinder same as for the FPD, the ECD detectors?
The pressure.
Gas pressure. Yeah, the pressure.
So the pressure from the generator is suitable for any other detectors, yeah. So for ECD, just on a note, for ECD we recommend trace nitrogen for the anode purge as opposed to the standard nitrogen. But yeah, the pressures provided by the generators are suitable for any detector and carrier gas. The EPC on the GC will regulate the pressure to the required level, and the generators generally are producing a pressure of gas over and above the required pressure for any GC method. So right, so I think there. Thank you everybody for attending and for your interesting questions. And if there are any further questions, feel free to email myself or Greg, or go to the website. There's a function there where you can send any questions in. So yeah, thanks very much everybody.
Thank you, Dr. Thank you, Greg. I think we can wrap up. We've answered most of the questions. If you would like to you send further questions, please just drop us an email and we'll revert back to you at the earliest. Thank you, everyone.
Thank you.
Thank you.